All right, thanks, Juan. So, yeah, I'm going to talk about this popular topics of observers, alpha parameters in the Hartle Hawking state. So, I would say we now, I think Ahmed described it very poetically as whatever, the first 2 decades of the 21st century or something. I don't know. We have a fairly robust way for thinking about the black hole information problem and the black hole interior. I wouldn't say we understand everything, but at least I feel I understand it better than I did when I entered the field. To summarize what we learned, well, maybe different people would write different summaries, but here's the one I would write, which is that the effective field theory of the interior is non-isometrically encoded into the microstates of the black hole, which leads to a page curve that's consistent with unitarity via the quantum extremal surface formula. Okay, so that's my attempt to have a brief summary of what we learned. Now, since we think we learned something, well, we should see what else we can learn. And in particular, since we're trying to do quantum gravity, well, the 2 things we're supposed to think about are black holes and cosmology. And so if we're happier with black holes now, let's try to think about cosmology. Unfortunately, when we do this, it leads to a kind of shocking conclusion, although maybe, I don't know, maybe by now everybody's numb to it, which is that the Hilbert space dimension of quantum gravity in a closed universe is 1. So in other words, in a closed universe, there are 0 degrees of freedom. And so what are we supposed to make of this? It doesn't feel like we have 0 degrees of freedom. You know, does this mean that we should that we've ruled out experimentally that we live in a closed universe? Or does it mean that we're wrong about black holes and we should give up the progress that we thought we made? Well, I'm not sure. And I will say this is a very confusing thing. You know, there are a lot of papers on this subject now. I mean, some by me, some by many of you. My confidence level in the things I'm going to say today is not 100%. So, I don't think anyone else's confidence is 100% in what they're saying either. And so, some degree of humility is in order. So my goal here is to have a discussion with all of you. Okay, not just during this talk, but throughout the rest of the week. Now, recently, some of us proposed that the problem can at least be lessened or ameliorated by treating the observer who's looking at the universe differently from the way you treat the rest of the universe in the fundamental laws of nature. And so there are 2 sort of closely related versions of this proposal and various modifications floating around. And the one that we did, the idea was that in the inner product in the fundamental Hilbert space, you don't actually use the standard inner product, which is somewhat trivial. The Hilbert space is 1-dimensional, but instead you use some additional structure to define a more robust inner product, basically by using a quantum to classical channel that decoheres the observer in their Poynter basis. And we argued that if you do this, then you can recover semi-classical physics up to errors that are exponentially small in the entropy of the observer. So this is a small number for us, something like e to the minus 10 to the 25, let's say, for me, I don't know. But it's a very big number compared to what you would have expected for the scale of non-perturbative quantum gravity effects in our universe, which would be something like e to the minus 10 to the 120. Okay, that's much smaller than this. So this is a large deviation from what we would have expected from sort of effective field theory analysis. Yeah, and so then if you, to relate to the other proposal, you take the observer entropy to infinity in an approximation where you treat the observer as a world line. So in these papers, the discussion was phrased in terms of transition amplitudes between arbitrary states. And the Hartle Hawking state did not play a very special role, which maybe was, at least to me, a little bit unsettling because, well, if you think that there's only one state, then that one state probably should have something to do with the Hartle Hawking state at least. And so it should appear more prominently than it did in these papers. And so my goal today is to rectify this and get the Hartle Hawking state there for you more explicitly and also understand how this approach relates to alpha parameters and the sort of 3rd quantized approach to quantum cosmology. And I also, at the end, will try to stir up some trouble by pointing out a puzzle relating these ideas to the string landscape and potentially identifying some tension between ADS-CFT and the path integral. So this is based on a paper that Ying and I are working on. Ying is going to talk more about this stuff, I guess, tomorrow. Okay. So let me start by reviewing what I'll call baby universe quantum mechanics, by which I mean the sort of third quantized path integral approach to quantum gravity, studied initially by Coleman, Giddings, and Strominger, and then really nicely formalized by Marolf and Maxfield a few years ago. I don't know, is Henry here? I don't think Don is here. I don't see Henry. Okay, all right. So this will be my interpretation of what they said, but I can't promise they 100% agree with everything that I'll say. So what's the idea? The idea of baby universe quantum mechanics is that you use the path integral to define an inner product between states with arbitrary numbers of closed universes. Okay, so here I'm looking at an amplitude between a 1 universe state and a 2 universe state. In general, they're disconnected contributions, so that goes into this aleph. That's their symbol, but I think it's appropriate. So the sum over all disconnected, vacuum bubbles is called aleph, so you divide by that to get a sum over connected amplitudes connecting different numbers of universes. And then you want to, so then the idea is these states that are labeled by configurations of some number of universes give a span of the Hilbert space, or strictly speaking, the pre-Hilbert space, and then you're supposed to quotient by null states to get the actual Hilbert space. So this is an old idea, like I said, going back to the 80s. Now, in baby universe quantum mechanics, there is a Hartle Hawking state, and it's just the state with no boundaries. So if you want to compute the overlap of the Hartle Hawking state with the 2 universe state, you put your 2 universe states here, these J's sort of label the configurations of the universes, and then you do the path integral summing over whatever you can put in here with no additional boundaries, right? So that's the sense in which the Hartle Hawking state is the no boundary state in baby universe quantum mechanics. And as usual, I've just drawn the connected contributions. I've neglected the vacuum bubbles. This is connected in some sense, because connected means that every component is attached to one of the closed universe boundaries. It's like with Feynman diagrams. So in the norm of the Hartle Hawking state is just this aleph. It's the sum over vacuum bubbles. And so if you want to normalize it, then you should divide it by the square root of aleph. Now, the main technical trick, which as far as I know was really introduced by Don and Henry, is that you introduce an operator on this Hilbert space, z hat of j, which creates an additional universe in configuration j. Okay, so acting on a state, say with 2 j's, with z hat of j gives you a state with 3 j's, where the new j is in the j that appears here in the label of the operator. And so if you think about it a little, you can convince yourself that the operators, these z of j operators, z hat of j operators commute with each other, because if you can just create a bunch of boundaries, and it doesn't matter what order you created the boundaries in, the path integral is going to be the same. And you can also show that the dagger of z hat of j is z hat of j star, where j star is essentially the CRT conjugate of j. Okay, and so that's implicit here, so that it was already on the previous slide. When something is in a bra, you put j star, and when it's in a ket, you put j. Okay, and so then the trick of Marolf and Maxfield is that since you have this big set of commuting operators, and actually they're normal operators because they commute with their daggers, you can simultaneously diagonalize z hat of j for all j, leading to what's called the basis of alpha states, which are eigenstates of z hat of j with eigenvalue z alpha of j. Okay? So that's the sort of lightning review of baby universe quantum mechanics. So at least in situations where these path integrals are well defined, which honestly is probably just in 1 + 1 dimensions, then these alpha states are really well defined. What I just told you is a mathematical algorithm, and you can derive from it a version of holography. So you take your favorite overlap between n universes and m universes, and you just insert a complete set of alpha states. And then since all of these universes can be obtained from the Hartle Hawking state by acting with z hat of j, then you can just use the eigenvalue equation to replace all of the j's by the eigenvalues in a fixed alpha sector. And so you just get an average over a factorized amplitude with probabilities given by the overlap of alpha and the Hartle Hawking state. Okay? And so the way you can think about this is you can imagine that, well, for each alpha, you have some fixed holographic dual where the amplitude factorizes between all the boundaries. And then this average over P I'll write with the bar. Okay, so maybe now here's a good time to comment on this notation that I've been using. So in the baby universe quantum mechanics Hilbert space, I write states with square brackets, okay? When I write angle brackets, those are states in the holographic dual, at fixed alpha. And then when I write a bar, I'm averaging over alpha, okay? So the left-hand side of this equation is what I would call baby universe quantum mechanics. The right-hand side is what I'll call average holography. And in fact, the wave function of each alpha state is completely determined by the z alpha j. You can compute it by using these formulas that I wrote down. And so at fixed alpha, for each fixed alpha, there's, for each set of eigenvalues of z hat, there's only one state, alpha, which means that the Hilbert space is one-dimensional in a fixed alpha theory. And so this is one way of getting at this conclusion that I mentioned on the first slide. Maybe not the most intuitive or direct way, but the way that is closest to our purposes today, right? Okay. Now, I want to be clear that although we can give these baby universe quantum mechanical amplitudes an averaging interpretation, I want to be clear that baby universe quantum mechanics is a conventional quantum theory. It has a Hilbert space, it has operators, and there's no funny business. So in particular, if you multiply two transition amplitudes in baby universe quantum mechanics, like say these two one universe transition amplitudes, you do not include topologies connecting this amplitude to that amplitude in the path integral, okay? In baby universe quantum mechanics, this quantity really is just the product of two numbers, and there are no wormholes connecting one amplitude to the other. And so here I've written that here. The path integral calculation of this factorizes into this thing times that thing with not like a wormhole going from here to there or something like that. Now, I sometimes encounter resistance to that statement. It's given all the progress in recent years with replica wormholes and so on, people always want to connect everything that you can with wormholes, and I'm sympathetic to that. But I want to emphasize that actually the most well-studied example of I didn't just make up baby universe quantum mechanics, neither really did Coleman, Giddings, and Strominger. It's the same thing you do whenever you do the world sheet approach to scattering in string theory, okay? And so if you consider a closed string scattering amplitude, and you compute the S matrix by summing over all the topologies, when you square the S matrix to compute a cross section, you do not include world sheets that connect S and S star, okay? Bad, bad, bad. You wouldn't do that. If you did that, the whole edifice of perturbative string theory would come crashing down, okay? And so I would say string theory, perturbative string theory in the world sheet approach really is baby universe quantum mechanics. And that's why the closed string Hilbert space is not one-dimensional, okay? If you included things connecting this S matrix and its complex conjugate, then you would have to conclude that the string Hilbert space is one-dimensional. Okay. Now, although factorization does not hold, okay, so good. Now, although factorization does not hold in baby universe quantum mechanics, it does hold, at fixed alpha or in a fixed holographic dual. Okay, in other words, so if we do one of these averages, then under the average, I'm allowed to take a 2-to-2 transition from two universes to two universes and split it into two one-universe transition amplitudes. Okay, I'm allowed to do that under the bar. I'm not allowed to do it, after the bar. So from this point of view, average holography, you can think of this non-factorization that I wrote, right, with this one, this non-factorization, as coming from ensemble fluctuations in the sort of ensemble of alpha states, right? So it's like this, right? If you look at the average, the bar of the product of two things, it doesn't have to be the product of the bars, okay? And that comes from fluctuations in the alpha ensemble. Now, the fact that ultimately things do factorize under the bar, in a fixed holographic theory can lead to disturbing conclusions, okay? So here's one kind of disturbing conclusion. So let's imagine in the holographic theory, let's try to compute the transition amplitude between two states J1 and J2. And for fun, we're going to compare that to just the norm of J1 and the norm of J2, okay? And then to make sure that we get something positive, we'll square it, although it's actually not really necessary. It's already positive without the square, but just to be absolutely sure we can square it. And then we can compute the bar to get something that we can compute using the path integral. Well, this path integral actually, all the terms in this path integral, they have the same boundary conditions. So they're the same path integral, and so we just get 0. So in other words, the transition amplitude between any two states, which are normalized. So if I normalize the states to set the two norms to 1, then this just becomes 1. And this is saying every transition amplitude between any two states in the holographic theory at sort of fixed alpha is 1. So of course, it's not surprising, right? This is just a consequence of the fact that at fixed alpha, the Hilbert space is one-dimensional. So of course, all the transition amplitudes are 1. Okay. I think, Luca, are you going to say more about this in your talk? Maybe you are. I don't know if he's here. Yeah, he says yes. Okay. So Luca will say more about this in his talk. Okay. All right. So that's it for reviewing baby universe quantum mechanics. Now I'm going to complain about it. Okay. So I said, I'm trying to start discussion here. I'm trying to give everybody stuff to think about. I'm confused. I want to share my confusion with all of you. Okay. So let me say why I don't like it. So there are a couple reasons. The first reason is because outside of 1 + 1 dimensions, or maybe borderline 2 + 1 pure gravity, the path integral is not well defined, right? This is 1 because gravity is not renormalizable, right? We have to view it as an effective field theory with a bunch of higher derivative terms. Probably only an asymptotic expansion in G Newton. And even worse, in some sense, the sum over topologies is also usually not convergent in higher dimensions. So that's asymptotic as well. And so this machinery of constructing a formal Hilbert space using the path integral and then diagonalizing the normal operator z hat to construct a set of well-defined alpha states is not well-defined. It's not something that you can actually do, even in principle. And I honestly, I think it's for the best, right? Like it would be kind of a pity if we could figure out all of non-perturbative string theory by starting with the supergravity path integral and running some machine. We can of course hope to learn about it, but it feels like getting the whole theory is sort of too much to ask, right? So that's one complaint, right? I really think you can derive holography from the path integral, except in these 1 + 1 cases like Sod, Schenker, Stanford, or using more generally using this Marolf Maxfield axiom. Okay, so that's complaint number 1. Complaint number 2 is that it's not holographic, by which I mean that the full Hilbert space has fundamental degrees of freedom, namely the alpha parameters, which don't live at asymptotic boundaries, which is, I think, something Jake and Kerman also emphasized in their paper. And moreover, I think that means it probably doesn't give a unitary theory of black hole evaporation, okay? Because, in the end, you're just doing the bulk path integral, and so in some sense, you're not really going to be able to compute. If you do the quantum mechanics of the bulk path integral, you're not going to be able to compute a unitary S matrix. You'll end up entangled with the baby universe, which, in baby universe quantum mechanics, the baby universe does have a big Hilbert space spanned by the alpha states, right? It's not one-dimensional in baby universe quantum mechanics. That's only once you do this thing of going to fixed alpha. Now, Don and Henry in their paper, they did talk about getting unitary black hole evaporation, but as far as I understand, they had to go to an alpha state to get that. And once you do that, you're sort of putting holography back, okay? Which is fine if you can really do it, but like I said, in higher dimensions, you probably can't really get the alpha states out of the path integral anyway. Finally, I don't think baby universe quantum mechanics is compatible with string theory, because in the sense that this is sort of another version of the previous complaint. So in string theory, we think every parameter is the expectation value of a field, right? Parameters are always dynamical. They're fixed by where you are, in the landscape. And in particular, that includes the gauge coupling and the n of SUN, and the NC, I'll call it, of SUN in n = 4 super Yang-Mills. So these things, you should really think of them as being part of J, right? They're part of the boundary condition in the closed universe. They're not alpha parameters. So for example, you can have a bulk geometry that interpolates between a closed universe with NC = 1000 and NC = 1001, by putting a Euclidean D3 brane in between, okay? And so I just want to comment because recently people have talked about maybe we should average over NC. So I don't know, maybe we should, but I just want to emphasize that you shouldn't think of that as an alpha average. NC is not an alpha parameter, right? Like n equals 4, and in fact the 2-0 theory and the ABJM and all this stuff are, right, they're all really part of the same theory. The difference between those is changing J and not changing alpha, okay? So averaging over CFTs is not averaging over alpha. Okay, that's one of the things I want to emphasize to everyone. In fact, right, since NC can change between amplitudes, like what does it even mean to average over? Like which one would you average over, right? If there's an amplitude that changes it from 1 to 100. So my view in light of all these complaints, somewhat, not sure what's the right word, orthodox, is that we should still look for some definite holographic theory with no alpha parameters, such as string theory, from which then we would hope that baby universe quantum mechanics emerges not as some fundamental thing, but rather as some approximate emergent thing in some appropriate limit as an effective field theory with a limited regime of validity, okay, which I think would have been a completely uncontroversial statement 15 years ago, but I'm not sure today. I don't know. You can tell me after the talk. And so what I'm going to do in the rest of the talk is I'll argue that by introducing an observer, it allows for baby universe quantum mechanics to emerge from a holographic theory up to effects that again are of order e to the minus s observer, and then I'll make some general comments about how holography of the path integral relate to string theory. Okay. So far this has been a bit high, abstract, so it's nice to have models. I like models. So I want to now go through this, put this stuff in practice using this simple 2D model. So it's a variant of the one introduced by Don and Henry, and then where you take just the Euler character as the action of 2D gravity in the bulk, but then you also allow for world line matter carrying some species index I. So in this paper, they introduced this modification with the matter. And the dynamics of the matter index is very simple. You just say that the species label on the matter has to agree at the start and the end of the world line. So the propagator is delta ij. So in this paper, we studied this model with one particle in a closed universe yesterday in this paper. But actually, for my purposes today, we're trying to connect to the Hartle Hawking state. This was not so fortuitous of a set of states to consider because because the propagator is delta ij, you can't have an amplitude to get one particle out of the Hartle Hawking state. So in baby universe quantum mechanics, the overlap between the Hartle Hawking state and a one particle state is 0. And so this kind of obfuscates the role of the Hartle Hawking state in this model. All right. So to get around this, what I'll do today is sort of the dumbest thing. I'll just consider two particle states. So you can get two particles out of the vacuum because they can be connected through a delta ij. For example, up here, the propagator could just do that. Okay. And so then the normalized two particle amplitude with the Hartle Hawking state is the hemisphere with the two particles plus that with a handle plus dot dot dot. And then if I compute an amplitude between two particle states, there's a disconnected contribution and a connected contribution. So in our previous paper, and I think also for the Berkeley people, this was 0 and this was 0. And so we just had this, all right? And so what I'm going to do now is try to dwell on how things change when you have this disconnected contribution. And so these are results, right? I mean, you can basically do calculations in your head in this model. So this is the full answer from this, that this comes from summing over genius, and then you get a delta ij from connecting these two with the propagator. Here, the disconnected contribution gives you a square of what you would have gotten from one of these, now with two of these delta ij's, and then this is the cylinder contribution where you have to sum over the ways that you could contract the indices here. Okay. Now, something I want to emphasize, and which we're going to return to repeatedly, is that the disconnected contribution actually dominates if I equals j and I prime equals j prime, because you get an e to the 2s naught here that you don't have there. Okay, and so this dominance of the disconnected amplitude is going to kind of be our foil for a lot of the rest of what I'm going to say. Now, to see how this factorization on the Hartle Hawking state relates to the one state in the fundamental Hilbert space, we need a microscopic model, right? Here I just told you the path integral, but in some sense this is after the average, right? So what is the theory before the average? So I'll use a variant of a code model that we had in this paper. So in this paper, we had a 1-0 code model where we had a random orthogonal matrix and we fed the state of the bulk into the random orthogonal matrix and then just projected onto the all zero state. Now that model is one where the overlap with the Hartle Hawking state is zero. So I need to get a disk amplitude that's not zero, I need to have two O's so that they can connect. And so here's what I do. I feed the state of one of the particles into this O, the other particle into that O, and I project onto some entangled state chi. Okay, so that's going to be my holographic map that takes some, bulk state or some, these I and J, they're like the J that I had before, and turns it into a number in the fundamental Hilbert space at fixed O. Because remember, the fundamental Hilbert space is one-dimensional, so every state has to get turned into a number. If the state is a ket, it gets turned into a number like this. If it's a bra, it gets turned into a number like that. Okay, and then I'll just, the fine print, I'll work in the limit. So these O's are D by D orthogonal matrices. I'll work in the limit where D goes to infinity. I'll fix the range of I and J so that these fixed states, psi naught, get bigger and bigger in this limit. And I'll also fix the overlap of chi with the unnormalized Maximally mixed state going here to be something called square root of k. That's just some parameter in the theory that exists in this limit. All right. Okay, so I won't teach you how to do these calculations in real time. I'll just tell you the answers. So if I consider the Hartle Hawking state with a two-particle state, that's just this number. And then when I average over O, I get the square root of k times delta ij. If I do an amplitude with two of these, right? So this is remember, this is a factorized thing because V turns this into a number and phi dagger turns that into a number. So this is a product of two numbers because we're in a one-dimensional Hilbert space. But then if I do the average to try to compare with baby universe quantum mechanics, then I get a leading term, which is this disconnected term, and then I get something like the cylinder here. And so at least at leading order for each index structure, this agrees with the path integral, provided that I take this k to be e to the 2s naught, right? So then this is the hemisphere, this is the disk contribution, this is the two disks, and this is the cylinder. Now the cylinder actually had a third term that was the same as this term, but I guess I'm viewing that as a small correction to this. Okay. And this agreement actually, so I did it here with just one boundary, but it works also with more boundaries. You can consider, with amplitudes involving 2 boundaries, 3 boundaries, 4 boundaries. However many boundaries you have, for each boundary, you just supply these numbers, okay? And then do the integral at the end, and you get a match with the path integral in this toy model. Okay. So in fact, this numbers, we can identify them in the sort of Marolf-Maxwell language this O is like the alpha parameters, right? We're averaging over the matrix O. So in this model, the alpha parameters are continuous. And the eigenvalue of z hat is precisely these numbers V acting on ij. Okay. Now, I want to emphasize that the one state in the fundamental Hilbert space here, at fixed O, is this somewhat complicated state. Okay, it's probably easier if you look at the picture, so let me go back. Right, so I'm taking the inner product of ij, which goes in here and here with, kind of everything above I and j. So there's a chi, 2 O's, and then this psi naught, and that gives you some messy state, which is the actual one state. And it's not the baby universe quantum mechanics Hartle Hawking state, right? That's this simple delta ij, okay? In the fundamental theory at fixed O, what you really mean by the Hartle Hawking state, and this is one of the lessons that I think we learned, is just the number 1, okay, right? The rule is for each boundary, I supply these factors, and so when I don't have a boundary, I just don't supply these factors, so I just have the number 1, okay? In the fixed holographic theory, that's the Hartle Hawking state, 1, all right? Okay, good. So now let's go. So we've now seen that an average over theories with a one-dimensional Hilbert space can reproduce the path integral. That's not so surprising. But we also have to deal with my complaint that really we don't probably have a bunch of theories to average over. We just have string theory, and so we want to have something that works with just one theory. Okay. And unfortunately, I argued that in that one theory, there's a one-dimensional Hilbert space for the closed universe. And so, you beg the question, how can we account for the richness of human experience in a one-dimensional Hilbert space. Okay, and so that's where the observer decoherence rule is supposed to help you. So I'm going to use this. Hello, so that's 5 minutes. Yeah. Okay. So I will use the observer decoherence rule to do this. Okay. And so in practice, what this rule does is, so the most enlightening way to say it is in terms of this channel, but for doing calculations, it's easier in practice to do something equivalent to using the channel, which is that you clone the observer out of the system in their pointer basis, which you can think of as establishing a Heisenberg cut between the observer and the system that they're measuring, as in the Copenhagen interpretation of quantum mechanics. And since I said interpretation of quantum mechanics, I'll jump quickly to the next slide. In our model, here's what the rule looks like. Okay, so we want to compute this averaged overlap between a pair of two particle states. So I put in the two particles here at the boundaries, and I sum over what goes in between. But then to implement the observer rule, I also have to include an observer here, which then gets entangled with this reference system that goes around out the outside. So I want to emphasize, because this causes confusion, the reference system is not real. Okay, it's just there to help implement the chain. Okay, so the observer is still here in the system. They're not outside. Okay, so you can evaluate this using the path integral. So it's pretty much similar to the answer we got before. There's the two disk contribution and the cylinder contribution. The only new ingredient is that here the observer has to come out of nothing, right? So there's an amplitude lambda, which is the amplitude to create an observer from the vacuum. And that, yeah, this is the same set of things I drew before. It's the cylinder contractions, okay? Now, I will call the observer Hilbert space KO, dimension KO, and to avoid excessive observer production in the vacuum, I'll assume that this amplitude to make an observer from the vacuum, lambda squared, is less than 1 over KO. Otherwise, you just kind of can produce all sorts of observers willy-nilly. Now, an immediate observation is that although the disconnected amplitude is suppressed by lambda squared, right, because you had the observer coming into those spheres, it's enhanced by e to the 2s naught. Okay, and so even though you have to pay a cost to nucleate an observer in the disconnected amplitude that you don't have to pay for the connected amplitude, the e to the 2s naught more than makes up for it, at least for reasonable sized observers. And so the dominant transition amplitude between a state where I'm here with an atom and another state where I'm here and the atom, say, decayed to another state, is that you defluctuate the entire universe and then refluctuate a new universe, okay, which is doesn't seem consistent with experiment, to say the least. Okay. Now, the alternative observer rule from Berkeley would actually ignore the disconnected contribution, right? It would say the observer can't connect through the two disks, and so you just shouldn't write it down. In this model, you get that if you really take S observer to infinity at fixed lambda, because then the lambda squared is small enough to beat the e to the 2s naught enhancement, but I don't feel this limit is so physical. I feel if this is the de Sitter entropy and this is our entropy, then we shouldn't be doing this. Okay, and then this amplitude is here, and we have to think about it. All right, so I'll talk more about that in a sec. Let me just quickly say that remember the goal here was to learn what happens at fixed O. The goal of the observer rule is to recover sensible physics at fixed O without doing an average. Now, I drew this small so you can't actually see this. To do the fluctuation of the inner product in the presence of the observer, there are 15 topologies that contribute. Here they are. Okay, but the answer is actually pretty simple. At large K observer, the dominant terms are these ones, which if you look at it a bit, it's actually just the square of the single amplitude from ij to ij prime, I prime j prime. So the ensemble fluctuations are suppressed by K observer, just as in the previous papers. And so what we learn is that the observer rule turns holography at fixed O into baby universe quantum mechanics, which is nice, right? So now we get baby universe quantum mechanics in a limit, but only up to things that are of order e to the minus s observer. Okay. Last two slides. So we've now seen that the observer rule allows baby universe quantum mechanics to emerge from holography without alpha parameters, which I like because I don't like alpha parameters. Okay. If you do, sorry, but I don't. On the other hand, the baby universe quantum mechanics that we got has this disturbing feature that the transition amplitudes can be dominated by disconnected factorization on the Hartle Hawking state. And I think of this as a version of the Boltzmann brane problem, right? Like the dominant way for things to happen is via fluctuation. Now, we could just hope that our initial and final states happen to be almost orthogonal to the Hartle Hawking state, right? That's a cosmological question. Maybe it's true. For example, in the model, we could have I not equal to j. But in cosmology, we'd like to have some theory of the initial state. And in fact, the Hartle Hawking state is the most appealing state to choose. Oh, the last thing is the most fun, though. Okay, can you just give me? That'd be fast. Okay, so I want to just give you something outrageous to finish with. Okay, so consider a landscape with one ADS vacuum and one de Sitter vacuum. And I'm interested in the sector of the theory with just one spatial ADS boundary. So the Hilbert space is just the CFT Hilbert space. Okay, and the sector with one ADS boundary. And the state I'll consider is a state in the CFT which has an observer sitting in the middle of empty ADS. So that seems like a pretty easy state to understand in ADS CFT, or is it? Okay. So what I want to do is, since I've got an observer, and I just argued I can use baby universe quantum mechanics when I have an observer, I want to compute the expectation value of an observable that gives 0 if there's no observer. It gives 0 if the observer is in ADS, and it gives 1 if the observer is in DS. So this observable tells you whether you're going to be in ADS or in DS in this landscape. In this particular state of the fundamental theory. And then since I want to condition on having an observer, I divide by the expectation value of the thing that's just 1 if there's an observer and 0 otherwise. Okay, last slide. So here's what the calculation looks like. The expectation value of Q has a term where you have, so here's the ADS with the observer that's put there by hand in the state psi. But then since I get 0 if the observer is in ADS, to get something in the numerator, the observer has to be in DS, so I have to fluctuate a de Sitter vacuum bubble, which in it has a de Sitter fluctuated observer. Okay, so that's what this is. On the other hand, in the numerator observer, I have to count both the case where the observer is in ADS and the case where the observer is in de Sitter. So I get z de Sitter over 1 plus z de Sitter, where z de Sitter is the sphere partition function conditioned on the presence of the observer. So it's e to the s de Sitter minus the mass of the observer over the de Sitter temperature. And this is very large compared to 1, which means that this is very close to 1, which means that the observer is almost surely in de Sitter space. Okay, we have a state of n equals 4. It's got an observer sitting there in empty ADS. But if we use the bulk path integral, it tells us that actually that's not where the observer is. The observer is in de Sitter space. And so if you're an observer living in string theory in this landscape with the two vacua, the place where you should find yourself is in de Sitter, and ADS CFT is useless. It's not relevant for the experience of any bulk observer. Okay, so maybe one, I don't know. You have to choose between the Hartle Hawking state and ADS CFT. I don't know. What do you think? Am I going to get thrown out of IAS or so? Yeah, okay, so that's all I had to say. So thanks for listening.
Hey. Yeah. Thank you for the nice talk. I just want to go back to the relationship between the two observer proposals. I think
this is so 6 months ago, man.
Yeah. You said no, nothing. Correct. Like, I would say that it's okay. First of all, I don't want to take any stance on which one is better because they're
no, I'm not trying to say that either. We're all trying to understand. We shouldn't be fighting over who's better.
My take is that they're both bad.
I'm empathetic to that. Yeah, most likely outcome, in fact, yes.
Recovering, it's correct to say that the Berkeley prescription is recovered from the MIT prescription in the S observer to infinity limit. It's true for the dimension of the Hilbert space. But for example, the Berkeley prescription just, the dimension of the Hilbert space of the observer in that case can be any. And the Hilbert space whose dimension you're computing is just the dimension of the Hilbert space of quantum gravity observer interacts with. So that's an example of why I think it's not, one is the limit of the other. I think they're computing different things, and it would be interesting to understand.
Well, so I think what I can say uncontroversially is that our path integral calculations become your path integral calculations in the limit that S observer goes to infinity. Now, we can discuss whether the interpretation changes in some way, but I think it's, for the calculations, it's just mathematics.
But as observer in our case, it's not that calculation. That's what I want to point out. So it's not the same.
Well, S observer doesn't appear in your path integral calculation.
It does.
I don't think so. Yeah.
We can talk about it later.
Yeah, so, okay, as you probably anticipated, a lot of these arguments happened in a cosmology Boltzmann brain context, over the decades. Don Page made a version of this argument here, not about holography, about saying observers and quantum mechanics are incompatible. And the resolution that I've always believed is that there isn't, in fact, a projector onto decoherent branches. Like there is not, in fact, an observable which tells you whether you are on a branch of a wave function. And so that would suggest here that a resolution would be that actually, I think the resolution is that de Sitter and ADS are not like different direct sum sectors of the Hilbert space. They're like made out of the same degrees of freedom. And so if there's some overlap, I can't construct the observable. You construct it on the last slide.
I mean, so here I'm trying to just use the path integral, right, because that's one of the lessons we learned. It's a path integral observable. It's like
I'm not sure it's a good observer.
In the path integral, it's a thing I can insert in the path integral and compute the expectation value. Now we can discuss is it observable, but
I don't know if it's a linear algorithm. Right?
Yeah, well, I mean, in fact, this calculation is happening in the context where I think that the closed universe's Hilbert space is one-dimensional. That's why I said that the fundamental Hilbert space is just the CFT Hilbert space.
Right, but in the string theory, for example, does it make sense to actually project onto observer and de Sitter versus observer in ADS?
Well, I don't know. In the path integral that we think is for the theory we think is dual to I don't know. In the path integral, I can do it.
In a cosmology with a landscape, right? You can't say, oh, I'm in one vacua versus another vacua.
No, but the path integral is a tool for studying that, like via the Coleman de Luce instanton and so on, right? Or at least the best tool we currently have. Yeah. Now, I mean, you might say that somewhere part of my interpretation in terms of holography here could be wrong. I mean, maybe hopefully, but it could also just be that this landscape is bad, right? I mean, this may not be how the string landscape works, right? I mean, probably it isn't. I mean, I think it probably has vacua like this and vacua like that. Sorry to the swamplanders. But it has a lot of other vacua too. And I could imagine that if you took into account all of them, it would change the result of this calculation. That's a hope that I have, but it's just a hope and it might not be true.
So on your last slide, where you do this calculation, I think you're doing the calculation in the way your guys' paper had done it. But if you do the calculation with the rule of you freeze the observer's world line and use it as a boundary condition of the gravitational path integral, then I'm not sure what calculation you're doing, because on the bottom, those two terms do not have the same boundary condition because they have different observer world lines.
So I'm allowing for you to be a fluctuated observer. Right. And so, I think that's part of the issue here is I think there's really two issues in getting from holography to something like quantum field theory and curved spacetime. One obstacle is this issue of ensemble fluctuations. And that was fixed by the observer rule. But then there's additional issue just within baby universe quantum mechanics of the disconnected contribution to things. And somehow that's the thing which I mean, somehow to me, that's just a feature of the theory. Like the theory if the theory predicts that observers are fluctuations, I'm a bit nervous to just ignore that. I feel like it's something we have to take at least a little bit seriously. Yeah.
So, sorry, I couldn't follow the details. So, so in this model where observer is fluctuating, does the observer see any deviation from quantum mechanics? Like is this small deviation or?
Yeah, so Ying is going to talk about this more in her talk, I think. So there's two things you could mean by that, right? There's questions about you set up an experiment right next to you and you do the experiment and you see what comes out of the experiment. So that's one way of testing the laws of physics. But and that I think it should be fine. That's what Ying is going to say. But if you ask questions that are about the world you find yourself in, like should I expect to see distant galaxies? Or should I expect to remember my parents? Or things like this, right? These are questions that are sensitive to whether or not you came from a fluctuation. And I feel like those questions should be within the realm of science. Like that, I mean, that is cosmology, right? We try to learn about the initial state of the universe, and it's a little different than trying to learn about the laws of physics right now. I mean, they're related, of course, but yeah.
In the first case, there's no correction or there's like small correction?
I think the claim would be in the first case there's small corrections, but that the universe that you find yourself in may not be consistent with the one that we live in, and then that's also a problem, right?
So presumably we live in a universe with multiple observers.
Mm-hmm.
different observers don't need a priori to have the same pointer bases. So what happens when, is there some phenomenon that brings observers' pointer bases into alignment when they interact?
Well, ours are pretty well aligned, right?
Well, right, but
Yeah.
in this model is.
Yeah, so I think you're supposed, the one you're supposed to use is the one that's you, right? So in a world with multiple, actually Elliot, is Elliot around? I think there's something. Elliot. Yeah, so in Elliot's talk, I think he's going to say a little bit about this, right? So the observer rule, you're not supposed to apply it to all observers. You're supposed to apply it to yourself. And so different observers can get different answers. And so we wrote this paper with Elliot and Netta saying that that's a kind of complementarity. Yeah. And then I would say that when observers can sort of classically communicate, then it better not matter which one that we pick. But if they're in disconnected universes, I don't know.
Okay, so we'll end here. We thank Daniel again.